thank you. Thanks also very much for being here, for inviting us. It was for me very spontaneous. Francisca contacted me last week. We have an ongoing collaboration since, or we know one another since 3 years now. We have a running project, let's say like this, since the beginning of this year. This was not running, the ideas are a little bit older, 3 years old, but this was not running due to a lack in funding. I guess most of you know these kind of problems that all of us may experience here and there. So yeah, so we are going to present, it's going to be a mixture. I'm a researcher here at the University of Aveiro at CESAM. Francisca is an artist with a scientific background. She is currently affiliated with, no, I forgot. So it's the Leibniz Institute in Berlin and the INESTEC from Portugal. I will start with a little bit of scientific background. Francisca is already here. Can you hear us already? No? Or can you also see us?
Can you hear me?
I can hear you also very well. I'm already introducing you, and I already forgot INESTEC.
No worries, you did it perfect.
So we are going to give a combined talk. I'm going to present first the research that we are doing here in Aveiro. Then I want to connect this research with the region of Aveiro, because we think that this region, especially the salt marsh, the RIA of Aveiro, is a very unique ecosystem. I also connect a little bit to what Monica said. So we have here, we are changing now a little bit the scales, or the dimension scales. We are now going to very microscopic organisms and structures that we find here in the RIA de Aveiro. Okay, we called this presentation now Cutting-Edge Photonic Nanomaterials in the Salt Marsh of Aveiro. I already introduced the two of us. What you see here on this micrograph on the left side, from you is the right side, are the shells of microscopic algae called the diatoms. The diatoms are microscopic algae. That means they harvest the sunlight with photopigments and use this energy to build biomass. And one particularity or peculiarity of these diatoms is that they produce silicon dioxide shells. And although these shells are transparent, silicon dioxide is basically glass, some of the shells here appear blue. And this is because the shells have highly periodic nanostructure interfering with incoming light. We call this phenomenon photonics, that is the manipulation of light at nanoscale. And now relating a little bit to Monica, you already mentioned the Green Deal. But let's be honest, the Paris Agreement, we are far from reaching it. Our consumption habits, our industrial practices are often in conflict with nature preservation. So could we use these diatoms, these algae, as an example to say, hey, there is high technology, there are advanced photonic materials available in nature. Can we learn how they work in nature? Could this inspire our own technology? But mainly, can this fuel arguments for the protection of these environments? So diatoms are really common. They provide roughly a quarter of global oxygen by photosynthesis. That is as much as the tropical rainforests. So it's not that we just find them here in Aveiro. We find them all around the world. On the left side, we see a living diatom cell with brownish chloroplast. This is typical for these type of algae. And when we remove the organic component of the cell, we obtain the silicon dioxide glass shell with highly periodic nanostructures. And then we could recently show that some of these structures work as what we call photonic crystals. In particular, I can go a bit further, we call these slab photonic crystals, and these are some of the most advanced photonic materials that we find today, useful for a variety of optical technologies, telecommunication, sensing, and among those technologies also the emerging quantum logic technologies. That means we could use, or we believe, we have not tested this, but we could use one of these structures and put it as a central photonic component into a quantum computer. Diatoms are evolutionarily relatively young. They emerged roughly 200 million years ago, but there are up to 200,000 species, all of which vary in the structure of the silicon dioxide shell. That could be a huge resource of innovation useful for a variety of technologies. I will now in the next slides explain a little bit, but relatively quickly, the scientific background. So the structure that we found in these diatoms looks like a split ring. This is the natural structure, not altered. If we look at the surface, it has a highly periodic surface structure. If we then look at the internal structure, we found even more complex three-dimensional porous systems. This, I believe, cannot be built with any modern nanofabrication techniques up to date. We then measured the optical properties, in principle reflectance. This will be a bit tough maybe to understand for people that are not trained for this, but this yellow line, what you see here is the reflectance, and what we can see here is called a photonic band gap. This is one particular property of a photonic crystal useful in these high-end technologies. We then, when we're talking about potential technological utilization, we have to consider aspects like reproducibility. In nature, we often find a variation of traits. All of us have a nose, but the nose of each of us is a little bit different, sometimes smaller, sometimes bigger. So if we look at 100 different structures, this is what we can see in the graph number A. If we look at different structures, different individuals of the same species, the properties are highly conserved. This is, from a technological perspective, very interesting. From a biological perspective, by the way, as well, because it might indicate that there is a biological function behind these structures, a function that we today do not know. So we have then also tested this structure. We show here exemplarily sensing. We have a sensing approach, or we use this structure to sense refractive index changes, or in this case, it was a gradient of glucose. And we can use this structure to sense as a sensor. So we can use it as a technological component. So the Ria de Aveiro is one particular ecosystem that is very rich in diatoms. There are plenty of diatoms, and there is a huge biodiversity of diatoms. So can we use this particular environment as a resource for innovation to inspire some photonic and optical technologies in the future? Could this help us to fuel legal arguments for the protection, first of all, of these environments, because to my knowledge, the Ria de Aveiro is not really protected, but using it as an example to show there are unique and there are really inspirational forces out in nature, things that we have not yet understood. On the left side, we can see, or we can get a glimpse on some of the nanostructural details. This is all nanoscale, so the pores here are roughly between 50 and some 100 nanometers in dimensions. And now I will come to the Icarus project, or shift a little bit to the Icarus project. Maybe first of all, how do we work in the scientific part? But this connects now to this art-science collaboration that we have with Francisca. So we go to the salt marsh, we collect the samples. We then need electron microscopes to observe these nanostructures that I showed you in the picture before. We then estimate, are they photonic, are they periodic? But in the Icarus project, we want to upscale these very tiny structures, which we can not see with the bare eye, and want to make meter-large sculptures out of this to bring it from the microscopic scale to the human visible scale. We then came up with the idea to use as a material ice. First of all, ice is transparent, like glass, so the material properties, at least from an optical perspective, are somehow similar. The second idea behind this is that ice is a very volatile material, so it melts. So we also want to create a narrative of environmental protection, and let's take care, it's in our hands to protect the treasures hiding in nature. And at this point, Francisca, are you ready to take over? I think I will continue here with the presentation. Can you connect, Francisca?
Okay. I cannot see it, but I know it. So
good.
We need just to be more or less tuned, and you just
we will try our
from
best.
Slide to slide, and I talk. But I'm ready whenever you are.
Okay, so I opened now here the front page from the Icarus project. Francisca?
Okay.
Francisca?
Okay, it's the first slide?
Yeah.
Okay, so First of all, thank you for the invitation and thank you for the introduction and for the nice presentation, Johannes. So I'm talking a bit about the research on the artistic aspect, and it's a bit similar, the approach. So you can go to the next one. I went with Johannes to do field trips. We collected together the mud. You can go to the next slide. We collected together mud, very smelly mud, but interesting. And
they are hiding inside here, so no one would expect that, right? Yeah.
And I got in contact also with the place, and I got in contact with the species and understood it a bit better. And then we brought this mud to the lab. I think it's the next slide. And then the glimpse that when you see in the microscope, and I think now I have a picture from the microscope.
That works quite well, I think.
I mean, I got super impressed by the photonic properties, the colors of the diatoms. And now in this picture, there's a lot. And next, there is a video. It's a not so good quality video, but you can see that the diatoms move. And you can also see that the diatoms reflect already a bit during the video. And this is very interesting because they have some sort of tropism to light. So they react to light and go in search of light. So on the next slide, I think we have this brainstorming where Johannes explained me the internal structure of the diatoms, and that this is the part of the girdle. I think it's the right name. It also has a next picture. And with this brainstorm and with this information and interesting characteristics and features of the internal skeleton of the diatoms, we came up then into using two main resources for the artistic project, that it's the ice and the light. So on the next project, on the next slide, I already have some images of the first experiments. Of course, before this, we did some experiments in our own fridges with a smaller scale ice. Some worked better than others, but this is at the ice factory that we collaborated with. So in case you need some ice for your projects, I can also provide the contact. So this is the tests done in the ice factory with already some sort of scaling, big blocks of ice. Of course, the idea is to make these ice blocks as diatoms, different species of diatoms. But that's the next steps. And I think I already have a video afterwards where it shows this beauty of the light, the reflections, and tries to explore a bit what might be happening actually inside of a diatom structure. So I think you can play the video.
Yeah.
You just let me know when it stops.
Okay, Francisca, it stopped.
Okay, so based on these experiments, we then tried to divide the Icarus project into two other ideas, that it was a performative approach and also as an installation. So then in the next slide, I show the performance approach, that it was this year at Sonar Festival. And in this case, we used 3 big blocks, also more or less in the same condition as the pictures before. So there's 3 main blocks. Of course, they are not the species, but ideally they are representing 3 species of diatoms We also included plants from Rio de Aveiro in the performance, and I have a snippet of a video. This is a 40-minute piece, was a 40-minute piece, but there is also a glimpse of a video, not so well good quality, but it helps to have an idea. I think we could play it. And the next two, it's two same approach as an installation only, as only the visual part. The first one was at this event at Tide Pool from Biotop de Relevanz at Kraftwerk Zurich, and this was just the main block left to melt, and again showing these reflections and refractions and the capabilities of the ice. This video doesn't have sound, but it's just to give an idea of the type of light interactions that we can get from the ice. And in the second slide, I don't know if the video already ended, but it's a similar installation. It's just in a bigger scale, in a bigger room, and we can see, I mean, there's also a video on the second slide, and we can see that different blocks and different sizes of the ice would also create different light reflections, and also when the light melts, the reflections are different. So we are very curious to see, when we apply this to the nanoscopic structures that we want to build, with the pores, with guiding the light with holes, how the light transmission will happen also when we really use the big upscale diatom structures. I don't know if we are ready, but on the next slide, it's our recent activity. Is it already there? Mm-hmm. Okay, this is for the European Union's Researchers' Night, and it's also a more educational aspect. This is the first three images are from also the factory, and in this time the plants from Rio de Aveiro were frozen on the blocks, and then they were left to melt at this beach during the day, also to call attention from vulnerability of resources, of biodiversity, of looking to these plants and looking to these species, like freezing them in a kind of important of heritage. So during the whole day, the blocks were there, left to melt, connecting with the place also. And at night, there's also a video then. We included the light part and the reflections and the interactions with the light. I think this also has sound.
Mm-hmm. I still want to finish the video with a Multicydo on the back.
Perfect.
Almost there.
I'm being too quick, sorry.
I was too slow. That is now the same installation in the night.
Okay, yeah. And with sound.
Okay.
Oh, sorry. And yeah, and with this project, I mean, I don't know if you want to add anything, but yeah, our goal is it's about translating this scientific, sometimes more complex contexts and upscaling, bringing them another perspective from an artistic point, while pointing the focus on nature and nature resources and biodiversity. So thank you very much.
And new ways, just to add, new ways to, or new arguments to protect it, no? Also, to find new arguments. Yeah.
Exactly.
Thank you very much.
Thank you.
Thank you, Francisca.